Hi ladies and gentlemen, today we're going to be graphing quadratics. We've been working on solving quadratics lately. We're going to set that aside somewhat. As I've been talking about in class, really we've got solving equations, we've got graphing equations. They go hand in hand, they work together. So we're going to be focusing on the graphing. Not so much on solving, although we are going to see a technique that we use to solve quadratic equations be really helpful today in helping us put together their graphs. So with that, we're going to jump in. We'll talk about standard form. Right away, we're going to see connections to things that you've already talked about in the transformations of graphs. So let's get started. So standard form from a quadratic. You know, we've seen quadratics look like different things, ax squared plus bx plus c. We're used to that one. Our standard form we like to refer to as f of x equals a times x minus h squared plus k. Now, why do we like quadratics in this form, particularly when we're graphing them? The reason that we like it this way is that we can see the transformations that we already understand take into place. We know what the a does to a graph. What does the a do? It stretches it, compresses it vertically, or potentially reflects it over the x-axis. The h and the k, minus h, what's that going to do? That's going to move our graph right h, the plus k, up k. So we can see the transformations that are going to happen. Now, with the graph of a quadratic, as you're familiar with, it's a parabola. And if we look at our parent function, the most basic function is right here, with the vertex at the origin, 0, 0. What is the vertex from our standard form? Well, we know that the a, like I said, stretch, compress, reflected vertically. Is that going to change where the vertex is located? If I stretch it vertically, does it change the vertex? No. How about when I reflect it? Does it change where the vertex is? No, it doesn't. So the a does not impact the coordinates of the vertex at all. What is going to impact the coordinates of the vertex is the h and the k. We know, like I just said, if we subtract h, we're moving it right h. If we add k, we're moving it up k. So if I take this parabola, our parent function, x squared, and if I move it right h and up k, to get our new quadratic, our new parabola, I should say, what are the coordinates of the vertex? They're hk. So when it's in standard form, we can simply look, identify the h, the k, and that's our vertex, h comma k. Our axis of symmetry. Parabolas, as we know, are symmetrical. They're an even function when centered at the origin. Y equals x squared. It's an even function. It's symmetrical about the y-axis. Now, what happens as I move that h to the right? Up k. It has a new axis of symmetry. And that axis of symmetry would go right here. And what is the equation of that line? Well, it's a vertical line, so we know it's going to be of the form x equals, and what is the x-coordinate of every point on that vertical line? It's h. So the h gives us our axis of symmetry. All right, parabolas can open up, they can open down. What would give us that? As we're familiar with our transformations, a tells us if the graph is going to open up or down. It's going to open up if a is positive. We know if a is negative, that reflects it over the x-axis, which means it would open down. There we go. So this is the important information that we need to graph quadratics in standard form. All right, continue on. Let's look at one. Find the vertex, axis of symmetry, and state whether the parabola opens up or down. So take a look. F of x equals 2 times x minus 3 squared plus 1. If I think about my standard form, a times x minus h squared plus k. We should be able to identify the a, the h, and the k. Just a reminder here with the video, I'm going to go through this quickly. You are totally free watching this to pause it, to back it up, whatever you need to do. But just to be efficient with time, I'm going to work through this quickly. Our h is 3. Our k is 1. So the coordinates of our vertex, 3, 1. The whole parabola is moving right 3 up 1. It's being stretched vertically by 2, but that does not affect the vertex. Okay. Axis of symmetry, as we talked about, the axis of symmetry is going to be x equals whatever the h is, the new x coordinate of our vertex. So our axis of symmetry, I'm just going to write AOS axis of symmetry, x equals 3. Does this open up or down? Well, we take a look at the A. It's positive. It's been stretched vertically by 2. Has not been reflected. So this is going to open up. Okay. Now I know I'm not taking the time to graph it, but hopefully you can picture what this looks like. All right, let's try another one. F of x equals x squared plus 4x plus 1. Uh-oh. Doesn't look like that. Doesn't look like standard form. What are we going to do? Give up? No. Okay. I need to get this in standard form. How am I going to do that? How can I get this to look like that? Think about that for a second. All right, now that you've had a second to think about that and I've quenched my thirst, okay, how am I going to go from there to there? Well, this is a quadratic of the form ax squared plus bx plus c. Notice this is a factored form, right? X minus h squared is x minus h times x minus h. So one of the things that I have in mind would be to try to factor this. Okay? But in factoring it, what I need is I need a perfect square trinomial. Okay? I want it to factor to x minus h squared. I want x plus or minus something squared. I want a perfect square trinomial. Do I know how to figure out a way to take a quadratic and get it into a perfect square trinomial? Of course I do. Okay? It's called completing the square. Okay? Remember how to complete the square? Let's get that 1 out of the way. Let's subtract 1 on both sides. Now this is a little different. Okay? We don't have a number over here. When we're solving quadratics and we're completing the square, usually there's a 0 and we're just subtracting and we're getting -1. Here this is f of x. This is like a y. Okay? So all I'm going to do is simply leave it as f of x minus 1. Okay, and ready, there we go. So I'll just leave that as f of x minus 1 equals x squared plus 4x. Now I'm going to complete my square. Okay, remember the rule, the trick, take the b, divide it by 2 and square it, add it on. Okay, we're going to take f of x minus 1. I'm going to leave a little blank right here after I figure out what I'm going to add on. What do I need to add here? Half of 4 is 2. 2 squared is 4. I'm going to add 4. So I'm going to add 4 over here. Okay. That gives me on this side f of x plus 3 equals, there's my perfect square trinomial. We know that's x plus 2 squared. Now, is this in our standard form yet? No, it's not. Standard form, f of x equals. We have f of x plus 3 equals. Okay, let's get that 3 back to the other side. And now we've just taken this ax squared plus bx plus c and gotten it into our standard form. We should easily be able to identify our vertex. That's the h to the k. Now be careful. H is -2. K is -3. Axis of symmetry is going to be the x coordinate of our vertex. X equals -2. And does this open up or down? Well, our A here is a +1. There's been no reflection. This opens up. So, fun to see how we took this idea of completing the square, which probably most of us just thought about as a way to solve quadratic equations, and we applied it to figuring out how to graph them. Cool. Let's try another one. F of x equals 2x squared minus 4x minus 1. Again, not in standard form. That's what I want. Okay, we're familiar. We're going to add 1. F of x plus 1 equals 2x squared minus 4x. Now, we know when we complete the square, we really like that leading coefficient of 1. So I'm going to divide by 2 on both sides. Starting to look interesting over here, but I'm just going to leave that the way it is. I don't have any issues with that. I could take 1/2 times f of x plus 1/2. No need to do that. I'll leave it just like that. Equals x squared minus 4x. Time to complete the square. Okay. What do I need to add on to complete the square? Minus 4x. So half of that, negative 2. Okay, this sounds familiar. Square it. We need to add 4. Now we know if I add 4 to this side, I need to add 4 there. The way that would look is I'm just taking what I currently have, and I'm going with a plus 4. Okay. I'll do that there. Now I have no need to do any simplifying there. I can leave it just like it is. I'll show you one more step. Let's get this into factored form here, and then I'll show you how we approach this. Let's see, that's x minus 2 squared. All right, now we want to get back to just the f of x. So we're going to work backwards. Let's get rid of the 4, get rid of the 2, then get rid of the 1. So subtract 4. Pretty simple. I suppose I should just show my work here. Wanted that blue. So subtracted our 4. That looks good. Now I'm going to multiply by 2 to get those to cancel. Now notice I have to multiply everything over here by 2. Let's keep going. That leaves me f of x plus 1. Over here I have 2 times x minus 2 squared minus 8. One more step, subtract the 1. F of x equals 2 times x minus 2 squared minus 9, standard form. There we go. Our vertex is at 2, negative 9. Our axis of symmetry is x equals 2, and this opens up. Good. Questions so far? All right. Hey, let's do one more like this. Just want to mix it up, just give you a chance to see something else that can happen. More repetition here. Hopefully it'll help. In fact, if you want to challenge yourself, you could pause the video, try this one on your own, then hit play to see how I approached it. So either way, whatever's best for you. I'll cruise through this. Let me subtract 7. Don't like that leading coefficient. Let's divide by 3. You know what? Thinking about that, that would give me a negative x squared. I'm going to divide by negative 3. That sounds better to me. That leaves me with x squared, be careful, minus x. So I'm ready to complete my square. Huh. B is negative 1. Can we handle some fractions? Negative 1 divided by 2 is negative 1/2. Squared, it's a 4th. Okay, not very often have we had to complete the square with a fraction, but hopefully this makes sense to you. Okay, that we're adding 1/4. Okay, that is what squared? X minus 1/2. And if you struggle with that, if that doesn't look right to you, test it out. FOIL this out. X squared minus 1/2 x minus 1/2 x. Perfect. That's our negative 1x. Okay, plus 1/4. Now let's get our f of x back. Okay, we're going to subtract 1/4. We're going to multiply by negative 3. Okay, let me distribute that. Plus 3/4, very good. And add 7. Alright, now I need to think in terms of 4 sevens is what, 28/4. Negative 3 times x minus 1/2 squared plus 31/4. Very good. Our vertex that's a minus 1/2, so moving it right 1/2. K is 31/4. Axis of symmetry is x equals 1/2. And this thing opens negative 3. That stretched it vertically by 3, then reflected it over the x-axis. That opens down. Awesome. Ready for a challenge? You know, sometimes instead of just repeating the same process over and over again, it's nice to do it once and for all. Can we get ax squared plus bx plus c into standard form? Can we do it for the generic equation so that we don't have to do this anymore? Okay, same steps. Let's follow it. Subtract c. F of x minus c equals ax squared plus bx. Divide by a. Come on. Iterate. Taking a while. Load, load, load. Save, save, save. Well, while we wait for this, it's kind of looking familiar already to something else we've done. Yeah, there we go. As I do this, see if it reminds you of anything, particularly when we get to the next step, which is completing the square. Well, how do we complete the square? We need to take this, the coefficient of the x, divided by 2 and square it. b over a divided by 2 is b over 2a. Square it, that's b squared over 4a squared. Sounds good to me. It should remind you of something. All right, let's keep going. This factors to be x plus b over 2a squared. Okay. Now I'm going to subtract this over. I'm going to multiply by a. I'm going to add c. Okay, multiply by a. A lot of writing, but that's all right. Our hands could use some exercise, right? Well, that's convenient. Add c. Ta-da! We did it. What's the vertex? Ooh, bad handwriting. Vertex, negative b over 2a, comma, negative b squared over 4a plus c. Now if I wanted, I could get a common denominator here. Actually, why don't I do that? That's a 4a over a 4a, so this would be really what? Negative b squared plus 4ac over 4a. That looks a little bit better. There's our vertex. Axis of symmetry, x equals negative b over 2a. Now, opens up or down, we know that depends on the a, so that's not something that we can answer at this time. But look at that. Okay? Our work with our generic quadratic produces a vertex of negative b over 2a, negative b squared plus 4ac over 4a. Negative b over 2a. That might sound familiar to you from prior classes. The vertex of a parabola of the form f of x equals ax squared plus bx plus c. The vertex can be found by taking negative b over 2a. Okay. Now, you can use this formula to find the y-coordinate, or you can simply plug this number back into the function to figure out the y-coordinate. But here we go. Okay, the vertex of ax squared plus bx plus c is located at x equals negative b over 2a. Okay, so I take a look at this one. Do I have to complete the square, go through the whole process? No, I don't. Find the vertex. X equals negative b over 2a. Now my a in this one is 1. My b is negative 4. This would be negative 4 over 2 times 1. X equals, what would that be? Positive 4 over 2, that is 2. The vertex is at x equals 2. Okay, let's get the y-coordinate, 2 comma, plug it back in. What do we get? 2 squared, that's 4, minus 8 is negative 4, plus 7, 3. Isn't that nice? Isn't that better than doing this? Okay. I'm really glad we did that. Thanks for doing that with me. Okay. Find the maximum or minimum value of the quadratic. Okay. Maximum, minimum. It's the highest or lowest point, right? Highest, lowest point in a parabola is going to be located at, well, lowest point if it's opens up, highest point. All right, sorry, got interrupted there. So the vertex, right? That gives the maximum or minimum. Okay, all we have to do is locate it and figure out if the parabola opens up or down to know if we got a maximum or a minimum. So, okay, quick note. Opens down. That tells us right away if this thing's opening down, we have a maximum. Okay, so let's find it. Vertex, negative b over 2a. Negative, let's see, b is negative 6 over 2a, negative 2. A lot of negatives. Let's be careful with this. 3 over 2, I believe. It would be 6 over negative 4. Perfect. Negative 3 over 2. All right. Okay. Now, to answer this question truly correctly, what is the maximum value? Is negative 3 over 2 the highest point on that parabola? No, when we talk about the maximum or minimum, we're really talking about the y value, aren't we? Okay. So what we want to do is we want to plug this in. Okay, f of negative 3 over 2 equals, you know what, I'm going to grab my calculator. Negative 2 times negative 3 halves squared minus 6 times negative 3 halves minus 1. 3.5. I don't know why this is taking so long to save. Okay. Now, forgive me on this. I just realized I threw the y-axis up here pretty lackadaisically. Our vertex is in the negative x values. Should have been like this. Okay. I don't know if I nailed it other than that. It's probably still off. But anyway, 3.5. Okay. The maximum occurs at y equals 3.5. There we go. All right, shall we do one more? Okay. All right, does this function open up or down? Leading coefficient, our a is 1. Opens up. Tells us we have a minimum. Okay. Let's find it. Vertex, x equals negative b over 2a. Positive 3/2. Now that is not the minimum value, that's the x value. Let's plug it in. F of 3/2 equals, I'm going to go back to my calculator. Three-halves squared minus 3 times 3/2 plus 1, negative 1.25. And we said that is a minimum. Awesome. Well, that was fun. Okay. Graphing quadratics, standard form is a nice way to work with it. If it is in the form ax squared plus bx plus c, we've got a fast way to do that using our x equals negative b over 2a. Okay. Have a terrific rest of your day. Thanks for watching.